usual good shape. Talking on the ferroelectric liquid crystals.
First of all, I would like to thank the organizer of this program, so I can participate in this program. I have been enjoying very much so far. What I'm going to talk about today is some mathematical analysis for ferroelectric liquid crystals. So I'm not really comfortable with presenting this material with many experts in this room. Okay, so what I'm going to here is the outline of my talk. First, I'm going to give brief introduction, and then give you some existence result, and then I simplified some geometry. It's very well-known book self-geometry. I will consider some partial regularity problem, and then I will consider very easy kind of model problem, and it's a very approximation problem, is one-dimensional problem, and then the last part is the I'm not going to discuss the lambda 두장 model, but this one or discussed I think 3 weeks ago. Okay, so first of all, I'm going to everybody know in this room about liquid crystals. I just bring this picture from the Wikipedia. I realized that many people use the same pictures. This is the nematic phases, and then molecules align in certain directions. But when you lower temperature further, then there is some one-dimensional formation of liquid crystal. This is translational order, and then you have orientational order. You have this is called schematic A. We need two order parameters, and then when you lower temperature further lower from here to here, then you actually get the some molecules tilted from the z-axis, and we call it schematic C. So there is another phases which is called chiral phases, and in this case, this is the chironematic, and this is actually chiroschematic phase. And what this one is, when you from the bottom surface and molecules align all these directions, but when you go along in z directions, the molecule kind of rotate around this z-axis, the chironematic, and then this next one is chiroschematic. Okay. And here is the picture I got from the web page, and I'm not sure how they obtain these beautiful pictures. Yeah, this is a very beautiful picture. I just wanted to show. I just put it here. And there is another schematic C phase, the chiroschematic. I already gave you the picture. So chiroschematic phases, there is some another polarization field, and in this one usually some n cross this gradient omega is a layer normal. And this one, I believe this one was discovered by Bob Meyer, 1975. And in this case, what happened is at the bottom surface, molecules tilt this direction, but when you go along this direction and the molecule turn around, still sitting on this cone and turning around this z-axis. And this one actually makes the three stable switching problems. So that surface is stabilized ferroelectric liquid crystal displays. So here is the switching. So when you don't have any electric field, then molecules have helical patterns. But when you apply electric field in certain direction, it's up or down. They all organized the same directions. But when you change the direction of electric field, and molecules align in these directions. So transition from here to here, then you actually go through this state. So this is famous three stable switching problems. Okay, here is the cartoon. This is a picture of the chiroschematic C phases. Suppose we have a layer normal is xy plane, and then there's a constant, the angle, molecule sitting on this cone, and then let's call this alpha, and then the polarization vector point this direction. So in this case, P is perpendicular to both molecules and then layer normal. Okay, so and then when you write psi is the translation order parameter for semantic, then you can rewrite using complex field, and then actually you defined n psi in this form is exactly rho square gradient omega. In that case, when you rho equals 0 is nematic, rho is constant, the semantic, but in general you don't have rho is not constant in semantic case. So there is another interesting material. So recently, many people working on this problem is the banana-shaped band core molecules. In that case, the molecules bend in this direction. Looks like bananas. In that case, how the model is, you connect to an endpoint, and then we call it, this is the vector n, and then there is a polarization vector in that case. In general, they are not perpendicular as in semantic C. And or there's some tilt angle between, there's some angle between P and n cross n psi. So in semantic C star cases, they are parallel, but in general they are not parallel. So okay, so we need to, in order to model these band core molecules, we need to consider these situations. And then we are going to put in the energy somehow this relate P and n psi, and then you can see a little bit complicated form in the later. Here's a picture I got from the web page too. There's some switching problem, very interesting switching problems. Yeah, so I'm not going to talk about banana-shaped molecules today, but just to show the pictures. Okay, so
banana faces in your presentation that are not chiral.
You mean this one?
Yeah, you consider non-chiral molecules too for the bananas.
Well, I'm not going to talk about banana-shaped molecules. I just showed the pictures. Yeah. Okay, here is the description. You already know everybody knows the liquid crystals you described by this is the unit vector n. And the semantic liquid crystals, we need two order parameters, n, the director field, and then psi, and the level set of omega corresponding to the semantic layers. And chirosemantic or band core molecules, we need three order parameters with n, psi, and then we have another p. And semantic C-star cases, actually, you can consider p as n cross gradient omega, or you can penalize that term, the 1 of epsilon square, and then you can penalize the terms. You consider p as independent parameter and penalize. So those are the same things. Your questions?
Yeah, you have this m psi. What does m psi tell you in addition to these parameters? Previously, you have defined m psi.
Well,
vector m psi. What is it telling in addition to this parameter, for example?
Or why do I need p?
No, m psi. Previously, you have defined vector m.
M psi. That we try to write down the layer normal using this psi function. M n psi is just a layer normal,
Okay.
not unit normal, layer normal. Okay, so here's the famous Osim-Frank energy. It's all the same, but in general, you also want to put B here is B vector, and chirosemantic faces B actually P, that's n cross K in general, and then we have some condition here, the conditions on coefficient. And semantic liquid crystals energy functional, we have polarizations, and then what happens is you have polarizations, divergence, P actually the charge density, and they create electric field, and then we put the Maxwell's equations here, and they will minimize this energy with respect to these conditions. Okay, here is the schematic energy. You have seen this one last week. Then we're talking about this energy, schematic energy functional, and then you have energy functional associated with the polarization vectors. There are many different kind of polarization term. This is the most simplest one. You can either consider the saturation cases, the magnitude of P is constant, or you can put a P squared and the fourth order term. When you consider antiferroelectric cases, you can put up to sixth order term, and then you can, if you want to, you can also put divergence P minus C0 squared, such like those terms. Oh, yeah. So there are many different terms. You can also have terms like divergence P dot curve P as the nematic direct field, and you can also found those terms from the Longar's paper, 1982. You have the terms by using symmetric argument. He found many different terms. Okay, here's the next one. This is the ferroelectric case, and this one I consider antiferroelectric cases. So what happened in the antiferroelectric cases? Each layers the molecules point up and point different directions. When you look at the average at the neighbors, and you got the zero, so continuum out of P becomes zero. You also consider P equals zero, then we consider antiferro. And then you have some P magnitude 1, then these ferroelectric cases. Okay, this is a typical electric field energy associated electric field. And then you need to put a -1/2 here, and then this interaction between polarization and E. So when you, sometimes I remember when I was a grad student, I usually I didn't put 1/2 here, and then I look at Maxwell equation, this cancels out. And then I realized the electric field is wave energy, and D is partial derivative, the partial derivative with respect to E is D, and then you actually get this is the energy, so I need to put 1/2 here. And for banana, say molecules, this is simplest form, and then we added these terms. This term originally got idea from Chris Bailey and Chuck Gartland, Tony Yaklis, and we reformulated those energy in this form. But today, so I'm not going to talk about this energy functional. Yeah, I don't think I don't have time for this. Okay, now just a brief some analysis that have been done for nematic energies and ocean-Frank energies. It was studied by Kindler-Lin, 1985. They proved for any ellipsis boundary conditions for n, there exist minimizers. This is one of for me, I think it's one of beautiful papers. And then what they've also proved, if n is in the minimizer, then n is held continuous except a closed subset C, which has a one-dimensional Hausdorff measure. So the reason why they consider Hausdorff measure is when you have a function, you can look at the Devil's staircase is contour functions. And you have a singularity. When you measure the singularity, and your Lebesgue measure, one-dimensional Lebesgue measure is 0, but when you compute the Hausdorff measure, the log 3 or 3, log 3 divided by log 2 somehow. So you have, and that's how they measure some structures with fractals. That's how they introduce Hausdorff measure. And in the special cases, you have K1, K2, K3, K4. This equals constant, K4 equals 0. Then the Frank energy reduces to the harmonic, the simple, just gradient, the n squared terms. And then the equation for n, set is this one, and this is famous harmonic maps. In that case, Schoen and Uhlenbeck, they proved n is a minimizer, then it is held continuous, in that case, except the finite singular point. So in our case, in Ocean-Frank cases, we one-dimensional Hausdorff measure is 0, but we don't know whether it's finite or not. But when you consider equal constant, then singular points are finite. Okay, here's a couple of days ago we were talking about the x. I should mention the at each singular point behaves like hedgehog. Singular point behave like x over x magnitude, and then you just rotation of this vector field, and then you.
How about discriminations?
No, Frank energy. No, does not allow the line defect. So then you have to go back to your lambda design model. Yeah. Okay, so this hedgehog is stable when K1 is less than K2. So in that case, they consider the domain omega is the unit disk with these boundary conditions, and this is and then if K1, K2, K3 satisfy these conditions, then this one is unstable. This is not minimizer. Right? So that was proved by Helene, 1987. And then also independently, I remember that Lin proved, S1 Lin proved that this is not minimizer if when K1 is just much bigger than K2 and K3. I remember they have some argument. I didn't check exactly, but the Coe and Taylor, they calculated the second variation of Ocean-Frank energy. And then they sort of used those arguments to prove this one. And here are the all papers work related to Ocean-Frank energies. And there is still open problems for theorem 2, and whether singular set is finite or not for non-general constant cases. Some people believe it's finite, but some other people also, I heard from some other people that they don't know exactly the answer yet. So the main difficulty is to prove monotonicity inequality. When you prove, when they prove the in that case, what they prove here, if it's minimizer, is held continuous except closed set, which has Hausdorff measure, and that in order to prove the singular set is finite, you need to use certain monotonicity inequality, and non-equal constant cases, symmetric energy does not have monotonicity inequalities. So I think this is still open problem. Okay, now I'm going to move on to symmetric liquid crystals. And here's the symmetric energy I already mentioned. Okay, I just rewrite just to show. Okay. And then here is some work done. This is a PD setting. Work done related symmetric energies. So you can see some more papers, and okay, I'm not gonna discuss this one. So there are some other works too. So now I'm going to talk about these energies, symmetric energies, existence of minimizers. And when you look at the symmetric energy here, this is a modified symmetric energy by Baumann and Phillips. And originally, this is similar to a Chen-Lubensky model. And then, in general, if we have C perp is negative, then it's okay. But C perp is a positive case. This energy does not have a minimizer. So we have is not bounded by lower from the below. So here is the one example. when you take the spatial psi function, then you compute the semantic energy, and it goes to m goes to infinity. This one goes to minus infinity. So this one is not lower bound in general. So, and then we have with Baumann and Phillips, we have proved the several existence results for minimizers. And first one is the Dirichlet. We have the magnitude psi is constant almost everywhere. In that case, we didn't have any problem. You can also have this one is a minimizer. And the second one has Dirichlet boundary conditions. Then still we are okay. So this energy has a minimizer. And then the last one, you don't have Dirichlet boundary conditions. Then we actually found some other energy, surface energy term. This allows, because of this term, this energy has minimizers. So when you have this Neumann type boundary conditions, this is surface anchoring, the weak anchoring problem, surface anchoring problems. So when you have these terms, we have minimizer, but we don't have this, then this does not have minimizer. So we also have some examples. So this is just the exister result. I'm not going to discuss this one. Okay. And then I'm going to move on to very simple geometry. I consider the layer is uniform in these directions, and then n sitting on this cone. And then I just rewrite my energy functional in terms of n, p. This is energy related to electric field, and I consider this Maxwell's equations. In that case, in this case, I consider n and p are all unit vectors. So I removed the penalty terms. And then I was very interested, and then I'm going to discuss some partial regularity for n and p. And without this p, and we know that the singular set has one-dimensional Hausdorff 0. And what if you consider these Maxwell's equations? So if you don't have p, then actually the result by Fanghua Lin, they proved the partial regularity results. But in that case, I also have p, this p on this too. So this is energy, my reduced energy. But this term doesn't hurt for partial regularity result. So this, in order to prove that we need this is the result I proved. If n and p is a minimizing pair, and this energy is certainly epsilon square, then for some r0, then this one holds, which means your gradient is like a c times 1 plus beta, and this means by using Morey's lemma, n and p are held continuous. We also proved this is held continuous except a closed set of Hausdorff measure 0. But here again, in particular, K1, K2, K3 are all equal cases, which is finite. But still, non-constant case still we don't know yet. So in order to prove this, we need several steps. I'm not going to discuss this. And what this one tells you is your energy. You have large balls and small half balls, and this energy bounded by these terms. So we did. This was argument by Fanghua Lin, Kindle Hart did, but we used some CR minimizer, local minimizers instead of global minimizers. So first step we showed this hybrid inequalities, and then we also need energy decay estimate, and using this one actually you can obtain this inequalities, and actually you can prove. So I'm not okay. So the thing is. The last thing I want to discuss is this one. if this one is greater than 0, so this is one of the ingredients to prove the discrete set. So when you want to prove if one is 0, if this quantity is greater than 0, that is called the monotonicity inequalities. But in that case, we have a certain different type, C minus C, S beta minus R beta. This one actually helps to prove the similar set. Okay, now I discuss the interaction between polarization and applied electric field. So what I'm interested in right now, and this is very complicated, I cannot actually analyze. In order to analyze, I look at the simplified geometry, or I take just terms, polarization terms, and applied electric field. And then after certain scaling, I reduce my problem. It's very simple. I don't consider Maxwell equations. I just applied E is applied electric field.
Could you go back a slide and tell us where that came from? Or just indicate what equation, what part of the energy that was?
Oh, which one?
The one-dimensional one. Just excuse me. You had a one-dimensional.
Oh, you mean?
Yeah. Are you going to show where that's from?
Oh, this one.
Just to indicate.
Yeah, I put it in here. I consider simple geometry, like bookshelf geometry, and then n sitting on the cone.
Okay.
And then I consider P as n cross gradient omega.
Okay.
And then I approximate it.
And U is what?
U is I don't exactly call this AC cosine, and there are some angles. U, yeah. From I think, yeah, angle like this. Yeah, I think I should have put 2 pi. One less. I think then pi. I think it should be pi. Okay. Then when u equals minus 1, I think it should be 2 pi. I'm considering 0 to 1, so I can, this u is the angle inside here. Yeah. And then I approximate it. So
sorry, I'm missing something, but in case the geometry is prescribed, isn't it a P related to N?
and that case P equals n cross K.
But then how is it different, an independent variable then?
Oh, in that case, oh, this geometry is not independent. The P and N described by this U.
So in the previous problem, the geometry was not prescribed. And the previous functional, yes.
When I proved there's a partial regularity, P and N are independent variable. But
they are related through the geometry, I would say.
they're related through the penalty terms. Yeah, we have a penalty term. We include penalty terms.
Which you have neglected in this approach.
Yeah,
This is somehow a relaxed problem with respect to the last one.
yeah, this is kind of the relaxed problem. Yeah, but for this one, I just consider P. In this problem, 1D problem, P equals n cross E3. Yeah. So when you decide the n, you can also then you actually get the P and n. So this is, and then I approximate somehow. So to make it easy.
So I didn't see it, but in the particular case when you have P independent of N, you still have a penalty that reinforces the minimizer to meet this geometrical constraint that we wrote. Is
Yeah.
that the case?
In the previous case, in this case.
With this case?
In the case for which you have started regularity,
It's,
Yeah, this one has a penalty term here. But
hold on,
shows
wait,
it's-
what is
It
it?
prefers that state, but it doesn't constrain it.
well, for this case, for study regularities, these are fixed numbers. So this doesn't affect on regularities. You can put other penalty terms. So when the problem is when you take epsilon was infinite zero, that's the problem. But for regularity problems, you can, yeah. For in that case, we don't have any penalty terms for P and n equals 1.
So basically there you have the penalty that P has to sit on the direction of the curve. So it's the K3 term is the one that does that will do the geometrical restriction.
Oh, you mean this? Oh, you mean this one?
Yes.
This one?
Mhm.
Yeah. For regularity point of view, this doesn't. This is fine. Okay, so we can add more terms for regularities. Yeah. So for the last problem, I consider n as like this: AC cosine and the 2 pi u, and then c sine 2 pi u. I should show the slide, but I have too much slide here, so I try to skip many steps. And then this is actually small. What I'm in this slide, what I'm interested in is to draw a picture the u respect to e, kind of hysteresis loop. I try to get the hysteresis loop between u and apply the field. And then in that case, I consider antiferroelectric case. In antiferroelectric case, you have potential function u squared, and then I got some other terms here. And then, so this is applied electric field. And then Euler-Lagrange equation for this is actually this, very simple. And I also consider periodic in g directions. So I got the u0 prime and the u prime 1 equals 0. So you can extend the periodically. So I'm very interested in periodic cases in that case. And then in order for this Euler-Lagrange equation has a solutions, we need the solvability conditions. You integrate both sides from 0 to 1, and you actually get the E. Electric field is nothing but the integration from 0 to 1 f prime ux. And then what I'm interested in, for any real number, I was interested in a bifurcation at that time. And for any real number alpha is in R, u equals alpha is the solution of original equations. For any real number u is solution of original equations. And then I was to realize, okay, I can use lambda as a bifurcation point. Bifurcation parameters. And then among many others, I can only consider solutions satisfying this average of polarization. We call it u equals lambda. U equals lambda, then actually satisfy this one. And I put this condition in these equations. And then I have some non-local differential equation. This is really non-local, and this is electric field actually the integral of f prime u from 0 to 1, and then I have this constraints. So actually, the electric field is actually Lagrange multipliers for this constraint. And then we have new energy. I eliminated the electric interaction between electric and u, and I got new energy, and I have a constraint. And then for Euler-Lagrange equation for this is the one I showed at the beginning. And for every fixed number lambda, E plays a role of Lagrange multipliers for this condition, this constraint. And I rewrite my Euler-Lagrange equation introducing this lambda plus omega w equals u, and then you rewrite this equation in terms of w, and I have these equations. Now it is lambda equals actually now in my bifurcation parameter. And then I look at, and then I rewrite this little bit implicit form, and when you right hand side I call it k w lambda. When you plug in this lambda and you differentiate this one twice, you actually get this. So this is my equation. And then I consider x is space C2 satisfying these conditions, and then I got z as this. And then using nonlinear functional analysis, and then I can define the function f as like this. This one is my function here. You divide by epsilon squared. And then also I define the g function as this. And then I differentiate, and then I consider you plug in w equals 0, and for any lambda, this g 0 lambda equals 0. So on real line, every point u equals 0, and then you got u, and you take u equals 0 here. Every point on this line is a solution of my equation. And this is a good way to start bifurcation analysis. And then I compute derivative of g with respect to w. Actually, I got these equations. And then using the simple eigenvalue bifurcation problems, and I can follow the argument of Krandall-Rabinovich's argument, and I can prove. And I can prove. Let's see. Yeah, first of all, I need to show this. So if epsilon equals small, and then I can find that there are some finite number of points whose Fredholm index equals 0, these are the bifurcation points. I'm not going to go into details, but somehow for each I can find the bifurcation point. At each point we have some pitchfork bifurcation point at each point. So either this or this. Okay, at each point, the bifurcation point, a pitchfork bifurcation point. And then it depends on the value of epsilon. Sometimes they come to pairs like this, 4 pairs. Because of f double prime u, this is fourth order polynomials. And then we have, sometimes you got 4 pairs of bifurcation points in the state. And then this is a local bifurcation point. And then you look at the global bifurcation point. This may go to infinity somehow. This goes to infinity. And there's some argument for bifurcation. This bifurcation is bounded, then it meets another bifurcation on x-axis and should meet some other point. And then you can actually get, finally you can actually get the using those arguments, you can actually obtain the bifurcation point for this. And I proved the for each point I can have a bifurcation curve. This is actually bounded. Then it meets another bifurcation point. So then finally I just give you a picture of this. So I have for given epsilon, I have in some cases I have 6 bifurcation points, and then this bifurcation point should meet the other one is here, and this is the bifurcation curve. And if I have this bifurcation diagram, and you can using the relation, the electric field is actually integral from 0 to 1 f prime u, and then you just calculate somehow. This is schematic pictures. It's not exact picture. Schematic pictures, you actually get this kind of hysteresis loop. And this one is another hysteresis loop. And when you, I read some articles when you produce hysteresis loop for N and P, and the inside they found another hysteresis loop. So here is the another bifurcation curve give another hysteresis loop, and this is the ferroelectric cases. And then in some other cases, you actually get certain two symmetric bifurcation curve, and this comes at the same time. What happens when you change the epsilon value, and these two bifurcations collide each other, it becomes one loop. And then when you draw a hysteresis loop for this case, you actually get this antiferroelectric hysteresis loop. When I do analysis, I was trying to draw these pictures. Hysteresis. I was very interested in hysteresis loop, and actually I actually get the prove this one, but it's not easy to prove this one. I can picture from here to this hysteresis loop, but I can actually prove exactly. Okay, this is the hysteresis for general cases. You have a ferroelectric cases, you got hysteresis loop like this. Polarization and E. You got antiferroelectric cases, you increase the E, then follow this one, you decrease, goes this way, and then come this way. And then you got for symmetric C-star cases, you got, I have one ferroelectric phase, and then you turn off the electric field, then actually you got healing of parents, and then you got opposite directions electric field give you this polarization field. Okay, so the last one, what I'm going to show is this. This one Perry discussed last time, so I'm not going to discuss it today. The last one I'm going to show is that I didn't prepare the. Yeah, I will give it the numerical result. This one I consider the same problem, and then I put some noisy terms, stochastic noisy terms. And then we were interested in a switching problem from one state to the other. And then I have one state, minus 1 to 1. A switching problem from here to there. This is all u equals 1 state, the u equals minus 1 state. And when you switch the electric field to the opposite directions, somehow this is the flat. Somehow there's some something bumps down and then it gives periodic structures. So we see there's some sort of periodic structures in the middle, and then we keep going, and then eventually get these structures. So this all depends on the time, evolution time, t and alpha. And then you can also see some here. It looks like some sort of the antiferro structures. Yeah, so this simulation work done with the G-Shen at Purdue with his student.
What are these pictures of? Are these solution branches or these?
Oh no! This one is a switching problem from one state to another. Yeah. U equals to 1, U equals to minus 1, and then when you change the direction of electric field, and actually that changes the molecular direction. So we are interested in switching problem, how switching goes.
Have you got space dimension on the x-axis there?
This is. Oh yes, 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 yes. This x-axis.
Sorry, what kind of dynamical equations?
Oh, there's a heat. Just the gradient flow. No, this is just the gradient flow. Okay, so this is the last. This is last part of my talk. Okay, thank you.
Questions?
Excuse me, when you have that helioelectric case, the thing is probably to light before than that.
Oh, not this one.
The next one.
You mean this one?
Okay, the last one. So you don't get, what is the reason? What is, say, the physics that doesn't give you any hysteresis loops in this case?
You mean over here?
Yes.
I think this one.
Why?
I think this is a kind of helical phases. You got averaged out for p. It becomes 0 in physics.
There's no surface stabilization in that.
Oh, there is no surface stabilization.
Otherwise, there would be
Mm-hmm.
hysteresis.
Now this picture is taken from Lagos books.
It's just,
Oh, okay.
it's just pulled.
Yeah.
Okay, you don't see the.
Now this is what I get. This is the picture from general picture from.
And in
Lagos.
your simulations, when let's see, when you do the switching, how does the surface stabilization comes in if you use that? What boundary conditions are you using?
What equation do I use?
What boundary conditions?
Oh, my simulation has Dirichlet boundary conditions. U equals 1 point minus 1, 1.1.
Okay, so you fix the state.
Yeah, otherwise it's very hard to do in computations.
And then another question: when you use that bulk function f in the part of the
6th order polynomial.
what is that parameter alpha? Do you know now?
Oh, that depends on temperature.
Okay, so that what phase transition is associated with?
That's antiferroelectric. Yeah.
But if you take that term away, you still get a quadratic energy. You still get a quadratic term. So is it absolutely necessary to get that?
Then if you remove alpha terms, you have the same, the wells for U equals plus or minus have the same wells. But when you, yeah, somehow if you change the, we have, for this case, this is 0, U equals 0, U equals minus 1, U equals minus 1, then alpha equals 0, they have equal energy. But when you change the alpha, then sometimes you have,
So in other words, alpha 0 would be the critical value. So you get a phase transition one side or the other.
you mean this one?
Yes.
Yeah, yes. Yeah.
Your very last picture of the dynamics there, the kind of oscillations in U, are they just transient? Or do you ever get a stable state?
Yeah, there's some oscillations in the middle, yes.
Is that transient? Or can that form a stable state where you have
It's not a stable state.
No.
It's a transit state. So I believe that when you have switching problem, and then when you have one electric field, you reduce electric field, I guess that it hits one of the solutions I found in the bifurcation. And it has some periodic structures, and then you reduce more than somehow. I think there is some relation between my bifurcation analysis and this simulation, but I don't have any clue how to prove it, but there should be some connections between two, I guess.
Did I get it right that in your bifurcation problem, the bifurcation parameter lambda is the total polarization
Yes, yeah, yeah.
My question is, how do you control such a parameter? Actually, at the end of the day, the total polarization is an outcome of your computation. In real terms, how can we be assured that a given value of the total polarization has been achieved? I might be missing something important here.
My simulation is not, it's kind of different from the bifurcation problems.
Now, just for the bifurcation problem,
Or you may ask about for the bifurcation problems, how do I control?
how do you control, in real terms, the bifurcation parameter?
I don't quite get the question what you're asking.
I mean, in physics, I mean, physical.
In physical terms, this is my...
How do I control in physics?
Is lambda related to the polarization?
global polarization.
Yeah, that's 0, 1.
This is an outcome of the memorization problem process. So my question is, how can you control?
Yeah, okay. In the literature, physics literature, how do I control it? Actually, I don't know. Yeah, this is some mathematical parameter for me. You may have some suggestions.
Okay, good. Well, thank you very much.
Thank you.